This is problem 29 from the photon. In problem 29, we have a 190 milliwatt laser operating at 650 nanometers directed onto a photosensitive metal with work function 0.7 electron volts. How many photons per second are emitted by the laser? Well, they give us the power of the laser with units of watts. A watt is equal to a joule per second. We can use the power that they give us in order to figure out how many photons are emitted per second. But to do this, we need to know the energy for the beam. They give me the energy, well, they give me the wavelength for a single photon, but I know that the energy for one photon is equal to, I can say Planck's constant times the frequency, or write that as hc over lambda. I know hc is equal to 1240 electron volt nanometers, but I want the energy of the photon in joules. So I'm going to go to my appendix and find Planck's constant in joules times seconds and the speed of light, and I'm going to put those values in for hc. So that gives me h is 6.626 times 10 to the negative 34th joules times seconds. The speed of light is 2.998 times 10 to the 8 meters per second, divided by the wavelength, which is 650 nanometers. Let's write that as 650 times 10 to the negative 9th meters. Then our meters will cancel out, our seconds will cancel out, and we get for this 3.056 times 10 to the negative 19th joules. But this is for one photon. The energy of the beam is equal to the number of photons in the beam times the energy of a photon. So the whole beam has a power of 190 milliwatts. The energy that you have is the number of photons. Let's call that capital N. The number of photons times the energy of one photon, which is 3.056 times 10 to the negative 19th joules per 1 second. So we can use this to find the number of photons, and we get 190 milliwatts times 1 second, which gives us 190 millijoules divided by 3.056 times 10 to the negative 19th joules, and that is 6.217 times 10 to the 17th, and the units cancel out, so that is the number of photons. That's what we were looking for, so that's our answer for part A. In part B, we want to know what is the maximum kinetic energy of the ejected electrons. Well, now I'm back in familiar territory again and can use my equation for the photoelectric effect, which says that energy of the photon is equal to the work function plus the kinetic energy of the electron. The work function was given to us here, and I found the energy of the photon here. I found the energy of the photon, but I found the energy of the photon in joules, so we could convert that to electron volts, but maybe it's just easier to say this is hc over lambda. Hc is 1240 electron volt nanometers divided by the wavelength of 650 nanometers, which gives me 1.91 electron volts. I'm looking for the maximum kinetic energy of the emitted electrons. That is equal to the energy of the photon minus the work function the energy of one photon is 1.91 electron volts, minus the work function, which is 0.7 electron volts, gives me 1.21 electron volts. That's the answer to part B. In part C, we want to know if 15% of the laser light is absorbed and 85% is reflected, what is the electron current in this experiment? Well, the current, as you may remember from Physics 261, is equal to the change in charge over the change in time, or if you stand at a certain spot and count how many charges pass by in a certain amount of time, that would give you the current. 15% of the light is absorbed. So earlier we found the number of photons that we had, but if only 15% is absorbed, only 15% of these photons are going to give energy to an electron. And remember that each photon gives energy to one electron. And so for each photon that we have, one electron will be emitted. So I want to know how many photons are absorbed per second. So I have the number of photons times the 15% per 1 second. The number of photons that I have is 6.217 times 10 to the 17th times 15% divided by 1 second. This is the number of photons absorbed per second, and this is equal to 9.326 times 10 to the 16th. Since this was 15% of all of the photons that we had up here, these are the photons absorbed per second. Each photon which is absorbed results in one emitted electron. So this is equal to the number of electrons emitted per second. I want the current, which is the charge per time. This is the number of photons per time. Each electron has a charge of 1.602 times 10 to the negative 19th. And so I have 9.326 times 10 to the 16th electrons per second times E, which is 1.602 times 10 to the negative 19th coulombs, and that gives me 0.0149 coulombs per second. A coulomb per second is an amp, so we can write this as 0.0, let's round it to 15 amps, which is what I was looking for.